Hello, everybody. Welcome to your video lecture for Monday, October 21st. I am still in Houston, so we will do video lecture today. I'm going to pick back up from where we left off on Wednesday, and I believe that was talking about um, developing a method. I'm going to do a quick review just so we can get into the flow. And so I believe we left off on Wednesday talking about some terminology. To be aware of in method development. Now I know we talked about all the different type of blanks already on Wednesday, but I still want to cover them again today, just kind of to make this video complete, right? So the first type of blank is called the method blank. What is a method blank? It's a sample containing all components, all components except the analyte and is taken through all the steps of a method. So you can think of a method blank like the blank that you would use when you're doing a Bradford assay. And so every one of those samples that you have of your standard will have a protein standard on it, in it usually BSA, bovine serum albumin at different concentrations, and the Bradford reagent. Well, your method blank for that particular assay will be the Bradford reagent without any uh, BSA standard inside. So you can think of the method blank as the blank that you would use in a Bradford assay that has everything in it except for the protein standard, and then you would treat that method blank the same way you would treat all the other samples. And so that's probably the most common type of blank that you'll be using in method development. The next type of method, the next type of blank is called the reagent blank. What is that? The reagent blank, uh, similar to a method blank. Similar to a method blank, but is not taken through all of the steps of the method. So a good example of that is if you were to have a blank that was DI water and you were to use it as a reference sample in a double beam instrument or something like that. But yeah, DI water would be something that would be a reagent blank if you had other components that were also in the sample as well that you don't have in this blank. And so the reagent blank again would be something like DI water. Next thing would be a field blank. Field blank. Again, this is similar to the method blank, right? It's similar to the method blank, uh, the but it's exposed to the sample site, but is exposed to the sampling site. So what does that mean? Generally, we will make a blank, prepare it in a laboratory setting. But if you're an environmental chemist, you would go get a field blank from, say, river water or something like that you know to be a clean river, and you're testing against a dirty river or a polluted river or something like that. But basically, a field blank is a blank that you prepare out in the field, whereas most other blanks that you would use are prepared in the clean environment of a laboratory. And so again, that's probably the most common usage of a field blank would be in environmental chemistry. Next term to be aware of is the matrix. What is a matrix? It is everything. It's everything else in the sample other than the analyte. And then the last one is spike. And what is a spike? This is also known as a fortification. Spelled that wrong. Fortification. And what that is that it's a apostrophe there. It's a known quantity of analyte added to a sample to test whether the response to the spike is the same as that is expected from the calibration curve. Example. Okay. Nitrate levels in drinking water are found to be about 10.0 micrograms per liter upon analysis. A spike of 5.0 micrograms per liter should result in an increase of, or increase to 15.0 micrograms per liter. If not, then the matrix may be interfering with the analysis. Whoops, spelled that wrong. Analysis. Right, may be interfering with the analysis. So there's a formula we could use to determine what our actual spike recovery is, right? And so, again, if you look at the example, if we have a sample of 10 micrograms per 10 micrograms per liter, we add in a spike of 5 micrograms per liter, we should end up with a total of 15 micrograms per liter. But if we don't see that, when we do our analysis in our calibration curve, that means there was something wrong with the interference. So something in the matrix that's interfering with the analysis. So being able to cover the 15.0 micrograms per liter from adding a 5.0 microgram per liter spike into a sample that has 10 micrograms per liter, that 15 micrograms per liter is known as the percent spike recovery, right? And so there's an equation to figure out what your percent spike recovery is. So that is percent spike recovery equals the concentration of the spike sample. So we'll call that big C. Spiked. Oop, that's a spicked. Sorry. Let's try it again. C spiked, right? Sample minus C unspiked sample. All that divided by the concentration added times 100%, or times 100 to get a percentage. All right. So the question then is, so what if the analysis resulted in a concentration of 14.6 micrograms per liter, what is the percent recovery of the spike? So we just use our formula, right? Percent spike recovery equals, and so it's the concentration of the spike sample, right? Which is what we got here, the 14.6. And that is subtracted by the unspiked sample, which is 10.0, right? Micrograms per liter. All that is divided by the amount that was added, the spike added, right? And that was 5.0 micrograms per liter, right? And I forgot to do the multiplication here, so I'll just do this. There we go. Multiply that by 100, and what we get is 92%. So that means that we had a spike recovery percentage of 92%, right? So what does that mean then when when you are developing a method? What does that mean when you're developing a method? Well, that means then, so if in your method specification, the acceptable spike recovery is between 96% to 104%, then the 92% spike recovery that you got in the example here is unacceptable. It's unacceptable. So, what that means is that something in your method or your technique requires improvement. Right now I spelled requires. Oops, spelled it wrong again. Requires improvement. Right? So just to review very important, this very important topic here, right? Uh, Say again, we are doing a nitrate analysis of drinking water, right? And the analysis said that you had 10.0 micrograms per liter in the sample, right? If you spike it with 5.0 micrograms per liter, you should come out with 15 micrograms per liter, right? 15.0 micrograms per liter after your analysis. So if you don't get that much, then there's something wrong with the analysis, something that may be wrong with the analysis, right? And so you can determine what your spike recovery is, percent spike recovery is, to figure out if you need to kind of redo your method development or maybe work a little harder on your technique, right? And so percent spike recovery equals the concentration of the spike sample that you determined using the calibration curve, subtracted by the concentration of the unspiked sample, divided all by the concentration of the added spike times 100. And so say you did this and you ended up with 14.6 micrograms per liter after the analysis. You can plug that into your percent spike recovery equation. And then so that is 14.6 minus 10, right? 14.6 micrograms per liter coming from the calibration curve, and then the 10.0 micrograms per liter from the analysis without the spike, and then divide all that by the amount of the spike added, which is the 5.0 micrograms per liter, times 100, and that gets you 92%. And so if you go through and get all that 92%, and your specification, your method says that the only acceptable spike recovery percentage is between 96 and 104%, then your 92% is not good enough. And so now you got to reevaluate your technique or your method. That's basically what that means, right? So there will be a quiz question about this that's going to be assigned for you. That's going to be due on Wednesday. It won't be too hard, but spike recovery percentage analysis is an important topic. Okay, so let's keep on going with some more terminology here, some new terminology. Next one is called the calibration check. called the calibration check, right? And this is analysis of knowns. Analysis of knowns to ensure that an instrument continues to work properly and the calibration remains valid. I don't know why we wrote the word unlike there, but it should say valid. Let me try that again. Valid. There we go. Remains valid. Okay. Another term that you should know, performance test samples. Performance test samples. What are those? These are also known as quality control or blind samples. We use those a lot when we test proficiency in not in just the instruments, but also in the lab techs as well, right? We'll give them unknowns that we know what the answers are already, and we check to see whether or not their performance is up to snuff. So yes, you do get the same kind of testing done on you when you move into the working in the lab that we do to you here in analytical chemistry when we say that you have to be within 5% of the known. So just practice for the real world, you know. So a couple of things to note. To gauge accuracy, we perform calibration checks. We also do the fortification recoveries or spike recoveries. We also do QC samples, quality control samples. That means submitting what are labeled to be unknown samples to your technicians and their instruments. But you know, as a supervisor, what the knowns are, and you can test to see how close the performance is to the known, which is what we do to you in the lab. Blanks too. How do we gauge precision? I always have to check this out to spell precision. I always get the I and the S mixed up. How to gauge precision? We could do replicate samples, which you've already been doing the entire semester. And we can also replicate portions of the same sample. Meaning we can use the same sample and do the same test on it multiple times, right? Or take from that sample, take from the same sample and do multiple tests on that, right? So these are, the first one here is all separate replicate samples, right? Whereas these are replicates from the same sample. All right. So next thing to talk about is assessment of quality control. QAQC, right? And what exactly is this? This is the process of collecting data to show that an analytical process or procedure or protocol I promise that says procedure, are operating within specified limits. This also means verifying that the final results meet the use objectives, right? And that's what I was meaning, or what I meant to said to you when we first started this chapter on QAQC about being fit for purpose, right? So how do we do this? How exactly do we do this? How do we do this? All right. A couple of things. We have this thing called the SOP. Does anybody know what that means? You can yell out if you're watching this on YouTube, or you could even type it into the YouTube comments. What does SOP stand for? SOP stands for the Standard Operating Procedure. Some people call it protocol. Either one is fine. Okay. We also assess QAQC by looking at documentation in laboratory notebooks. Oops. Uh-oh. Laboratory notebooks. I told you laboratory notebooks are important, right? And then any tasks that are done with a manual, right? A manual are monitored, right? They're monitored and recorded, right? Monitored and recorded. And so what that means is that you can have your procedure that's written in the laboratory notebook, but say you're working on a protocol that is like for a kit. For those of you in my lab, you use those protocols to do the plasma prep kits and the gel extraction kits, right? I tell you to write those protocols into your lab notebooks, but say you did write them to your notebooks and you're reading them straight from the manual and doing the protocol yourself, straight from the manual, then these procedures that you're doing that are outside the standard operating procedure must be monitored and recorded. So that's what they're talking about there. And then probably the most common way of kind of assessing whether or not you have a good level of quality control is using a quality control chart. Control charts. And so an example of a quality control chart, the one that I see most often in the both in the forensic labs and in the medical testing labs is called the Levy-Jennings plot. Levy-Jennings plot that is based on the Westgard rules. Not the Westgard rules, that's weird. The Westgard rules. I forget how to spell Westgard. There we go, Westgard rules. Right? Based on the Westgard rules, right? Okay, so let me draw you an example of a Levy-Jennings plot. This one was based on a urinalysis, right? So it's kind of important to get some straight lines going on here. Well, that's pretty straight, I think. Straight enough. And then, so on the x-axis, we'll have analysis date, right? And then on the y-axis, we'll say this is the urinary per chlorate levels, right? And so the unit here is uh, let's see here, it will be ClO4 in nanograms per milliliter, right? That should be milliliters right there, not microliters. It almost looks like I wrote volume there. Let me just write that again. There we go. Nanograms per milliliter. Okay. And so I wish I had some lines on here, but that's okay. We'll just do the top one here to be 6.0, right? And the bottom here will be 4.0. The midway point in between will be 5.0, right? And then between here and here will be 5.5, and then between here and here will be 4.5, right? And so you can see just based on the axes that a Levy-Jennings plot will chart over time the deviations that will happen to a urinary perchlorate, well, not just urinary perchlorate, but any kind of analysis. And you can see how much the known concentration deviates. And if it deviates enough, then maybe it's time to check to see what's going on with your sample, right? So let's see here. This is going to be a little hard to draw, but let me see if I can get it going here. All right, so at 5.0 all the way across, right? This will be the mean. This will be the mean. Actually, I should put it there because I need to draw other things there. So let me erase that real quick. You know, while I'm at it, I'm going to fix this too because that bothers me right here. There we go. So go ahead and fix that real quick. Oh, it already looks better. Makes me feel better already. And so this here will be the mean of the spike mean of spike of 5.0 nanograms per mil of the ClO4 minus, right? And then we'll do some dotted lines right here. Right, and another set of dotted lines right here, right at the 4.5. The other one was at 5.5. Okay, and then right between this two, we'll put another set of dotted lines here, which is the 4.75. This is definitely easier to draw when it was on PowerPoint as a picture, but that's okay. And then we'll draw another set of dotted lines, a dotted line right here at the 5.25, right? And so you might be asking yourself, what is the what do these lines mean, right? So the two lines plus or minus 0.25 from the mean of 5.0 nanograms per mil are the warning lines. So this is a warning line. And this one right here is a warning line. Okay. And so the one above is equal to the mean plus 2 standard deviations divided by the square root of n. And the one below the line equals the mean, it's supposed to be mu there, sorry, minus 2 standard deviations divided by the square root of n, right? And then the two dotted lines that are plus or minus 0.5 away from the mean of 5.0, these are action lines. All right. So the action line above is equal to the mean plus 3 standard deviations divided by the square root of n. Don't forget to put parentheses around these. Sorry about that. And then the one below is equal to the mean minus 3 standard deviations divided by the n. Right? And that should already look pretty familiar to you, because that means that the guys here for the warning lines, right, represent the 95% confidence level, right, or 2 standard deviations away from the mean. And then the lines that are the action lines, right, the lines are the action lines, those are the 99% confidence level, or 3 standard deviations away from the mean. 3 standard deviations away from the mean, right? So after drawing out this plot, right, let's actually put in some data and see what we're doing here, okay? Okay, so let's start out on our first day right here, and we are slightly above the mean on the first day. And so just to be clear, this is the mean of n equals 5 replicates per day. Okay, and so you see that this average here, this mean of 5 replicates per day, on this day is still below the warning line, right? It's still below the warning line, so there's no need for concern there. Let's say on the next day, it's below the warning line, which it's still below the warning line, and we're still good there. Let's say the next day after that, we had a particularly good day, and it's almost exactly at the mean line, right? And then we had another day where it's a little further away from the mean, right? But it's still within 2 standard deviations from the mean, right? It's not outside yet, okay? And so we're okay. We're doing okay so far. So we'll just keep on connecting the dots, right? And then the day after that, we go back up to close to the mean again, right? And then the next after that, we go even further, closer to the mean again, right? We go back down a little bit. And this is like the one time I will allow you to connect the dots, because that's what a Levy-Jennings plot is. It's connecting the dots, really, right? So we're going back down a little bit here, but this time, the next day, we go above the mean, but we're still within 2 standard deviations of the mean. So no concern there yet, right? And then the next day after that, we do our quality control checks, and we go back down a little closer to the mean. That's good, but we haven't crossed it yet, so we're still doing pretty good here. And then the day after that, we go down below the mean. But we're still within 2 standard deviations of the mean, so no need for concern there. And then we go up again. Now we're sitting right on top of the mean, so that was a good day of replicates. But for the last few days, I don't remember how many days this is now, but it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, it's not drawn to scale. But the last week, all of our quality control checks show a mean of urinary perchlorate levels that were within within 2 standard deviations of the mean of the spike, right? Which is good. Uh, then after that week, oh darn, we dropped down with our 5 replicate means. We're exactly on the line of the warning line. So maybe nothing. Maybe you don't have to do anything just yet. Maybe we kind of write this out and see what it looks like tomorrow. But a warning line means that you need to keep an eye on this. Maybe your instrument is starting to get out of calibration or something like that, and you have to redo the calibration curve, right? So it's starting to be a cause for concern. But then, oh no, the next day comes by, right? We already had the previous day was sitting right on top of the second, the 95% confidence interval line, right? The previous day. So the next day, though, man, the mean jumps all the way up to the action line, right? Uh-oh. All right, now we are 3 standard deviations or away from the mean, or 99% confidence level, uh, right? And remember what I said in statistics, it's like the opposite. You always think that having a 99% confidence interval level is better than a 95% confidence level, but in statistics, you want to have a smaller area, right? And so under a Gaussian curve, and so 95% is kind of like the limit for most people. So you've gotten here to 99%. This is action now, and so once you get to an action line, right? You're at the action line. There is something really wrong here, and you need to go through and reevaluate your methods or your calibration. So basically, you get a you get uh, an average or a mean of 5 replicates on this day, and it's on the action line, right? It means it's time to take action. Means time to take action. And the most common thing to do when your instrument goes way out of whack like that, or way out of limits like that, is to recalibrate the instrument, right? Is to recalibrate the instrument. And look at that. After recalibration of the instrument, you're back down to close to the expected mean of the spike, right? Of 5.0, right? And so that's good. And then you kind of hover around there for a while, and then you're there. And then, oh no, the next day you go past the warning line, but you don't hit the action line. So no need for, I mean, you should definitely be keeping an eye on it, right? But again, when it's past the warning line, but not hasn't interfered or hasn't encountered the action line yet, you really just need to keep an eye on it and see if it kind of stabilizes for the rest of the readings. So the next day comes up, and now you're within 2 standard deviations of the mean again, so that's a good area to be in. And now it's stabilizing around that area right there, right? And so after recalibrating your instrument because of this one action line, average or mean that you got here, right? But anyway, that's the point of the Levy-Jennings plot, right? It's for you to be able to go through and chart over time, over a period of several days, the mean of all the mean of all the replicates that you do for that day, right? And as you track them, you can see if they're deviating at all uh, from what should be the expected value, right? Which is, for this particular example, you did a spike of 5.0 nanograms per mil of chlorate, perchlorate, in the urinary perchlorate samples, right? And so you expect then that the average of 5 replicates of that spike should be around 5 nanograms per mil, right? And on the Levy-Jennings part here, you start out pretty good, but one of these, after about a week, it goes completely out of whack. You're outside your limits. You've hit the action line with one of those uh, sets of replicates, all right? And so now you need to go through and reevaluate or recalibrate your instrument. And after you've done that, you normalize again. You're back to being pretty close to the mean of the spike of the 5.0 nanograms per mil of perchlorate, right? And so over we will have Levy-Jennings plots that go for months and years, and we can track and see how our instruments are doing. And again, if they ever waver in their means, right, and their averages uh, to the action line, or close to the action line, but not actually encountering the action line, we'll start to reevaluate or recalibrate our instruments, right? And this helps us see uh, what it's supposed to happen. It also lets you uh, narrow down any kind of errors that you might have, systematic or otherwise. So, after having drawn this it's not a complicated chart, right? Because if you have a picture of it, it's fine, right? It's just drawing it by hand is difficult, but once it's drawn out, it's a pretty easy chart to understand, right? We just want to stay away from the action lines. We want to stay within 2 standard deviations of our mean, right? And that's a good thing. So let's go ahead and write some concluding thoughts about this. Control charts monitor performance 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 on blanks, calibration checks, and spike samples to assess results stability over time or to compare the work of different employees. Oops. Sorry. Employees. Here we go. They can also monitor sensitivity and selectivity if a lab encounters a wide variety of matrices. Right? So if a lab gets samples that contain all kinds of different components, that's what it means by wide variety of matrices. And oftentimes, different components can really gunk up an instrument, make it all dirty, and make it less sensitive, right? And so, if you get a lab where the same instrument is being used to analyze a multitude of different samples, and your Levy-Jennings plot starts to show some deviations from the mean, then it might mean that you need to clean your instrument, right? And that actually happens a lot, especially on LCMSs. We've had to clean our LCMS multiple times to actually have it working correctly. So I would like to just state a couple more definitions, and we can go ahead and end this lecture, and you'll have a quiz on this information posted soon, right? So the next word, the next phrase or term important here is method validation. I've already thrown around this term to you multiple times because you've already done it, and it was when you did the uncertainty budget for the balance and the micropipetters and the burette. That is a form of method validation. So what is the formal definition for method validation? Well, the formal definition is this: the process of showing that a new procedure or an existing one applied can't even read that. Let me write that again. Existing one applied to a new sample meets specifications, plural, and is fit for purpose. I promise you I can spell. Oh, there it is. Maybe I can't. There we go. Fit for purpose, right? And so when we come back after on Wednesday, I'll go into talking about linear ranges, dynamic ranges, and limits of detection. Other than that, just watch out for your quiz. That's coming. That's going to be posted soon, and it'll be due by the beginning of class on Wednesday. Thank you, and I'll see you all on Wednesday.